So we're going to start talking about kinetics. Kinetics is looking at how a reaction happens, how quickly. We're going to kind of look at mechanisms, what steps does it take, and what conditions has to happen. So what we've done so far, you did an intro activity, and hopefully the goal from that, there's a couple goals with why you are having to put nuts on a bolt. One, you were supposed to, when you're graphing in a perfect world, the first time you did it, I think most of you came up with a pretty linear relationship. It gave a pretty linear. The second time, not so much. But look at what happened. You added some different factors. When you threw in a different size nut, what you should have seen was that as you were going, ideal world, first time you should have gotten a pretty linear. And it was decreasing because you were doing it by how many of the nuts were left. Ideally, and some of you can kind of share yours, it should have maybe looked more like this. And what was happening is it was getting slower as it went because you had more of the ones that didn't fit compared to the ones that did fit. And so it was more of a logarithmic function. So that was why you took the natural log of it to try to find a linear relationship. Okay, granted, it wasn't perfect because we have human factor in there. Some of you were just faster than others. Some of you were slower than others. But this was what we were just trying to introduce, is you can look at data, and from the data, you can calculate things about a reaction. But there's a lot of other factors affecting it. So the introduction, I just wanted you to listen to the guy because a lot of times, like I said, hearing it from a different perspective is good. Now you can take your note packet and let's kind of go back and read. We're going to talk some about repeat some of that and go into a little bit of detail and do an example, and then we're going to go into how to determine rate laws. So kinetics is all about telling us if a reaction can thermodynamics tells us if it can happen. We haven't done this yet. Okay, delta G is predicting, and we're going to say it's spontaneous if this delta G is negative. We will be coming back to this. So what this tells me is these are both spontaneous, but spontaneous does not mean instantaneous, because this is how diamonds will start to decompose. But like we said, thankfully that doesn't happen very fast. Kinetics then tells us that it's going to be extremely slow reaction. This is what we're focusing on. It's not, can it happen, but it happens. Tell me, how fast does that reaction happen? Okay, so the first thing we're going to talk about, and this is what the gentleman was talking about, and sorry I don't do cool videos and jogging through pyramids and cornfields, but the reaction rate is just how much it's going to change over time. And we're going to use this a lot. Remember, brackets means concentration. That is that's our shorthand for concentration. And concentration is always in moles per liter. Okay, this time can either be in seconds, or minutes, sometimes hours, depending again on the rate. So it's never assumed. Always go back and double check the time. I've seen people miss points because they had the wrong time, just automatically put seconds. It's not always in seconds. Let's kind of do a shorthand then, kind of sum up of looking at the reaction. If I have A plus B going to C, let's just be very generic here. So what I know then, these rates, we want to know how are they going to change. Well, my rate then is going to be equal to, and we do say 1 over A in, change. I'm really bad at forgetting my change. Remember this, delta means change. So if I forget, you still put it in. So it's the change in concentration of A over the change in time equal, it's going to be, this is also going to be changing at a ratio of 1 over B. How much is that reactant going to be used up in that much time? Going to be equal to, now, so we are going to be losing this. Okay, it is still a positive quantity. the negative sign is just representing that you are losing it, or that concentration is decreasing. So you will be forming products, which would be positive then, at a change in concentration of C over your change in concentration of time, and the value of this product, so it just depends how many you have, see, almost forgot my triangle, over your change in time. So if it asks you just about a rate, okay, think about physics. Oops, sorry about that. But think about physics, not in a happy way, kind of. What is speed? It is a rate, and it's a miles per hour. Okay, our rate is in molarity per liters. Molarity per seconds, or molarity per minutes. How much is it decreasing or increasing? And so that again, the negative just means it would be a reactant. So if you had a product, then if it's a product, it's going to be positive because you are increasing the concentration. So this is why when you look at the slope, so look at this, if a negative slope, that has to be a reactant because it's getting used up. You have a positive slope, that meant it was a product because you are making it. So it makes sense, in the beginning you have 0 products. It hasn't started yet. And you have all reactant. So in this rate, notice what's happening here. It's not a linear function. We're going to actually start, not today, but start looking. We're going to manipulate data, kind of like you did with the screws, and that's our goal. What do I have to do to this data to make it linear? Because we like it to be nice and linear. Linear is easier. But what you can do, it's just like in physics, you can calculate an average rate. If you know at the beginning, a final and an initial, you can have an average rate. We can also calculate an instantaneous rate, just like you did in physics, that you can take the slope at that point. The slope at that point would give you an instantaneous reaction rate. So they change with time, but we always have to, this is where we not as much as physics, because we always say we start with our initial conditions because it's too hard to try to take concentrations in the middle. Now some of the ways we're going to change concentrations, not change concentrations, measure. We could do it with pressure if it's all gases. This is one way they can measure what's changing. Colorimetry. How does that color change? Because we know with Beer's law that if you see a change in concentration, you're going to see a change in the color. pHs. If you're producing an acid or using up an acid or a base, you would see a change in pH. So these are just different ways that we can determine how a reaction is changing. So I don't have this in there, so find a place to write this example. On the back, I don't know if we have a back empty, but beside your graph you could look at this. So here's an example of just looking at reaction rates. So here's I have 2 moles of dinitrogen monoxide becoming 2 moles of nitrogen and 1 mole of oxygen. So when it says express the reaction rates, this is where we're going to use our generic. So you just know the rate then would be equal. Well, this is going to change at a 1/2. This is my A's. At the change in concentration of this reactant over change in time, it would be equal to the positive formation, and again, this is a 2, this is where my 2 comes over, of the change in the nitrogen over change in time, that is a triangle, which would be equal to how much oxygen, well it's 1/1, that's why I do not have to put 1/1, how much oxygen is being formed in the same amount of time. So that is just the rate of reaction. How much is changing over how much time? Well, look at now we can get some numbers. So in the first 15 seconds of the reaction, 0.015 moles is produced with a volume of 0.5 liters. What is the average rate of the reaction during this time interval? If you need to pause it so you can write it down, do that. Okay, remember brackets means this means concentration. This is given in moles. This is going to happen a lot this semester. You need to really pay attention. So I need to have concentration, which is moles over liters. So first you're going to have to get the concentration. So you have this many moles, 0.015 moles in 0.5 liters. Therefore, your concentration is 0.030. I'm keeping my significant figures, and this is what the molarity is of that oxygen. So what's the average rate? Okay, well, rate would just be final, so whatever your concentration of your oxygen final minus the concentration of your oxygen initial over how much time. So now I know my final concentration, 0.03 molar. Again, we start from initially, so you had nothing to begin with, and that happened in 15 seconds. So then you just plug it into the calculator and you have a rate of 0.002, and what's your units? This was the change in molarity per second. Okay, you can have molarity, or a lot of times you just see it as moles per liter per second, because moles per liter is molarity. These mean exactly the same thing. You're going to see it both ways. Okay, I don't know why it's ABA. Obviously, this would be C. Predict the rate of change in the concentration of the dinitrogen monoxide during this time interval. Okay, you're going to come back up here. Look at this relationship. So I know then you're going to get -1/2 changing of your N2O over change in time is equal to the rate that the oxygen is being produced, change in time. Okay, so we know the oxygen value, so just now we're just going to plug in. So -1/2, okay, again, the change in the, this is why I forget it, I just get tired of writing it, but I do it, equals, what do I know, it's 0.02 molars per second. So then all we're doing is you need to solve it, so times both sides by 2, because you need to get rid of it. Now you don't have to worry about this negative, because we know we were just losing it. It's still again, remember, it's a positive quantity. The negative just means that's how much it's going to be decreasing. The negative would be decreasing, so don't let that freak you out. So what's 2? So the change in concentration over change in time would then, is this going to change in a concentration of 0.004 moles per liters per second, or molarity per second. It's easier to actually say moles per liters per second. And again, the negative is still there. It just means that that's decreasing by this rate. So every second, the concentration would be decreasing by 0.004 moles per liter. And look back up here. Doesn't this make sense? Well, yes, it's a 2-to-1 ratio, so you expect the rate is going to decrease at double the amount. So you're going to lose 2 of these for every 1 oxygen that's going to be formed. So that makes sense. So if it's just talking about the rate, then it's just how much you are producing or using per time. And that's not that bad. Looks kind of like physics. We don't use it as often, I'll be honest with you, because we tend to not know our concentrations quite as well like this. And you'll see this problem once, twice. What we tend to see more then is not the instantaneous. Forgot that slide was there, but I don't want to start over. The instantaneous slide would just be the slope. Okay, this is even rarer, I'll be honest, but you can do it. More conceptual, would just ask you how would you find the slope. Not going to show up on a multiple choice, because unless the numbers were really easy. Again, this doesn't tend to be our focus. What we tend to look a lot at is finding the rate laws. So what this graph would be finding the instantaneous rate, just that's like physics. Yay, don't tell errors I said it's chemistry's like physics. I don't want to get in that debate. So we always don't talk about the rate then. What we talk a lot about is a rate law. rate law. So this law is a big hint if something is different. So the rate law or rate equation, typically you see it as rate law. Determine the rate law for the reaction. Rate laws always have to be determined experimentally. Okay, this is huge. It has to be experimentally. So again, look at, I have my generic equation. These are my molarities. Okay, look at the difference. With a rate law, they are not the same. You cannot use a balanced equation to determine your rate law. Now, they might coincidentally be the same, and sometimes they are the same. That just is going to be determined by the rate determining step, which we will talk about in a couple days, but you don't know that. And so you can't just look at a balanced equation and know if the way it's looking, if that's the rate determining step or not. So you cannot just use a balanced equation. You cannot use a balanced equation. Did I say that? You cannot use the balanced equation to determine the rate law. The K is just some constant. So typically this is what it looks like. Rate equals K. Most of the time we don't worry about what K is unless it says determine the value of K. You just put in K. Okay, little k. It's a little k because we're going to have a big K in the next unit, which stands for the equilibrium constant. So different constants. And we need to figure out then, the goal is, what are these exponents? How do we figure out these exponents? They can be positive, negative, though I'll be honest, most of the time what you're only going to see are whole numbers. They're going to be integers. Typically, we don't see larger than 3. They could be halves. I haven't seen that in a long, long time. That was back in the 60s to 70s on those tests when they were a little bit meaner. They're not as mean anymore. Numbers tend to be more friendly. Okay, this constant is determined just by the reaction. It changes with temperature, so this is why in all rate law problems they're going to give you temperatures. It's just going to be stated in the problem. You don't do anything with the temperature, but the reason is that rate law is only good for that temperature, so that's why temperatures are going to be in the problem. If it's a very fast reaction, you're going to have a very large K value. So that's one thing you can kind of use to get an idea of if the reaction is going to be fast or not, is if that K value. The exponents is what we're going to call, we determine that it's called the rate order. So if it ever asks what is the order of the reaction, they can ask you two things. They can say in regards to A. So in the reference of A, look at the exponent. Again, we assume this is 1, we just don't write it. So you would say it's first order in A. Okay, look at the second. So this is on the B, so you just say it's second order in B. The overall rate order, add them together. 1 plus 2 equals 3. So we say this is a third order reaction rate overall. So when it talks about what rate order, you're looking at the exponents. You have to use a rate law to figure out the rate order. Okay, these units of K can get a little hairy, and this is the one time on a free response they will ask you, and they'll tell you specifically, and you get a point just for figuring out the units of K. Well, look at this K. Let's figure out. It depends, so all that we've done here, I know if I have this rate, I'm using the same one that I just had. Okay, let's solve for K. So that's what we got here. We just rearranged to solve for K. Well, plug in rate. Rate, you know, is moles per liter per second. Okay, here A is in moles per liter, B is moles per liter, but it's squared, so it's mole squared per liter squared. So if you multiply these two together, what do you get? Moles cubed per liters cubed is going to be over moles per liters per squared. Now we need to simplify, so when you have a fraction on the bottom, what do? You flip it. So to get rid of this, you're going to times it by liters cubed over moles cubed. So what this is going to cancel out, leaving you a second. Moles will cancel out, leaving you a second. So this is how we came then to this. liters squared over moles squared per second, because this per second didn't change. Okay, and this is why we use instead of molarity. So you could, and they would take it, but it's, if you notice, it's not molarity anymore. It's an inverse. That's just, you don't see that as often. You just don't see that as often. So it'd be the inverse of molarity, and that's what this is showing you. So this is why you tend to see it liters squared over mole squared per second. Wow, do we have to do this every time? If only there was a shortcut. Oh, there's a shortcut. Okay, so when you do it, what you do need to know that it's the inverse of molarity. Just know that K is going to be liters over moles, and remember, it's time. I don't know. It could be seconds, it could be minutes. You have to look at the rate to know what the units is going to be here. Now this X, the way to figure out X, it's just going to be one less than the overall rate order. So X is one less than the rate order. So if it's a third order, that's like that last one was a third order. So 3 minus 1 is 2. That's why our exponents were 2. If it's a second order, it would be liters per mole per time. Okay, if it's a first order, well, 1 minus 1 is 0. If I have liter to the 0 over mole to the 0 times time, well, anything to the 0 power is 1, and this is why it would just be a 1 over time. Okay, remember the whole reason for this K having to, it's being times, it has to equal, rate is a mole, molarity, moles per liter per time. So that's why your units of K have to cancel out enough of the concentrations to leave you with this rate. So if I had some crazy, if it was a fifth order, you would say fifth order minus 1, so excuse me, it'd be to the fourth, moles to the fourth to your time. Okay, is this a shortcut that's worth knowing? Yes, yes it is, because it can help you to figure that out. Like I said, that can be a point because they could ask you for the value of K. So what kind of data are you going to see? What you have to look at, they're going to give you, like, typically it's in charts or tables, and they're saying, okay, we did this reaction. And we looked at how much one reactant changed, and we were able to figure out the rate that it changed. So then we played with the reactant and then saw how it changed the rate. So what you have to remember is we're looking for an exponent. Remember, it's an exponent. So if you doubled, so let's just say you doubled the rate or you doubled the concentration, this happens a lot, you doubled the concentration, and what are you going to say? Oh, it went from a 0.1 to a 0.2. You doubled the concentration and it doubled the rate. So you ask yourself, well, 2 to what power is going to be 2? X has to be 1. X has to be 1, so it's a first order reaction. Okay, well, if you double the concentration, so again, doubled it, but you saw the rate quadrupled, you would say, well, 2 to what power is going to give me 4? That would be a squared. It would be a second order reaction. Are we seeing a pattern? Seeing what we have to do? Okay, I doubled it. This time I looked at it and nothing happened. You didn't see a change. Excuse me, it wouldn't be a 0 change, it would be nothing happened. If nothing, oops, it would be 2. It didn't change. Excuse me, there we go. And it would be 1. I was confusing myself there. You doubled it. So you have this doubled, and it was 1. The only way to get it 1 is if it was a 0 order. That means that reactant wasn't part of the reaction order because it must not have been in the rate mechanism. And we again will talk about the rate mechanism. So that means it's not in the rate law. So sometimes you won't have all the reactants in the rate law. They just may not be in that rate determining step. They're not really important. They're important. They're just not that so important in driving the speed of the reaction. Okay, so this is what it's going to look like when we're looking at these. So we're on page 3. Very similar. So look at what they're saying. This is saying that we had 3 experiments. So this just stands for experiments. Typically you'll see that. It could say trials. So they give you multiple trials. Okay, what you have to find is where did you hold one constant? And I know that my rate law is going to be some k, and it's going to be a to the x, b to the y. Don't use these. Sometimes it works out, but you don't know that. So find first where you hold one of the reactants constant. So look at trial 1 and 2. You held a constant, didn't change. So you ask, okay, what did I do to b? B doubled. Okay, B doubled. You look at now at your rate. It's kind of like an if then. What if? Well, if I doubled B, my rate doubled. So you're asking yourself, okay, 2 to what power is going to give me 2? So that's a first order because 2 to the first power is 2. So you say B is first order. So you just figured out the exponent for B. Now we need to figure out A. So find where B didn't change. So look at trial 2 to 3. B didn't change. So now you have to say, okay, I'm keeping B constant. A doubled. What did my rate do? That's a factor of 4. How do I know? Well, 8 divided by 2 is 4. Okay, we're going to do a lot of mental math here that you ignore decimals. And when I ignore decimals, I also like to ignore zeros. You could say 80 divided by 20, or we could say 8 divided by 2 is 4. Notice I'm ignoring my decimals. I'm really good at doing that. And that's what you need to focus on. The numbers are typically pretty easy on this. So 2 to what power gives me 4? That's how I know, well, 2 squared is 4. That's telling me then A is a second order. So my rate law for this reaction is just R, rate is K, A to the second, B. Okay, this time, oh wow, it did work out. Coincidence, we don't know that. It's not always going to be that. So what is the overall rate order of this reaction? It would be third order overall. Okay, let's go down below. Now notice there's only one reactant here. So we just kind of say, okay, what just happens if I change it? So the first one, what am I doing in that first trial? Well, I double it, going again. Ignore the decimals, so just going from 5 to 10 is doubling. Same thing over here. I ignore exponents and coefficients. 12 divided by 3 is 4, so it was quadrupled. So this would tell me it's a second order. We have another trial. Let's double check. I also doubled it from this trial. So what's 48 divided by 12? That is 4. So that just confirms that it is a second order. So the rate for this one would just be a second order. So you would say K, concentration of A squared. Notice there's no 2 at all in my balanced equation. So you can't just look at the balanced equation to determine the rate law. Okay, this is the back on top there. Not on top, but over. Sometimes things look a little weird. You have to figure them out. They're not always as easy looking through it, but you're going to be able to figure it out. So first, look at it. Find first where something stayed constant. So in trial 1 and 2, B was constant. So you ask yourself, okay, how did A change? A was doubled, and your rate doubled. So 2 to what power is 2? Tells me that A is first order. Okay, now the problem I look at, I don't see anywhere where A is held constant. But you do already know what rate is for A. So we already know A is a first order, and we can use that fact now. They'll never change everything. You're going to have to at least be able to figure out one. So look at between trial 2 and 3. What happened? A doubled. Well, I already know that if A doubled, it's a first order. I know that. So what did B do? B also doubled. But I'm trying to figure out this. So what you're kind of asking yourself, okay, what did this do? It doubled. Okay, it doubled. Well, the only way that you're going to do this, that you're going to see that this doubled, but this doubled when you already know that A was a contributing factor, the only way that could be is if this was a 1. And the only way this could be a 1 is if it was a 0 order, which means B is not part of this rate law. It has no effect. So the rate law for this, then you leave out the B. So even though you have a coefficient of 2B in the rate in the balanced equation, it is not in the rate law. So this is why it's so important to use your experimental data, and that balanced equation doesn't tell you what is happening. You have to use the data. And so that's where if you know one, you can still figure out the other one because it's a cause and effect relationship. Okay, pause it. I want you guys to try it and then start it back up and we'll see how you did. Okay, so the rate law, generic, find where did it change. You can decide which one you want to start. I'm going to start. I started. You could have done it different between trial 1 and 2. B kept constant. I saw that A doubled. And I didn't see any change with that. That's telling me A was not involved. I doubled A. It didn't change your rate. So therefore, A is not part of the rate law. Then look at what happened between trial 2 and trial 3. You held A constant, B doubled, your rate doubled, so this time B did have an effect. So you know that it is first order in respect to B. So this rate law only has the reactant B involved in it. So they're not always everything has an exponent. You have to figure it out. Okay, just a couple more. This one is probably how they're going to look more often. No, we do see A's and B's. We're going to just use real compounds. So what you just have to do is be careful that you just write them down, put the right exponent on the right reactant. And again, you look, what can I see constant? So trial 1 to 2, ammonium is staying constant. What happens to your nitrite? It doubles. Okay, now look at this in the math. Don't let these numbers freak you out. When I say I ignore numbers, what I see when I look at these numbers, I see 27 and I go, what is 27 divided by 13.5? That's 2. Don't worry about all these numbers. Mental math, when you can do these in multiple choice, simplify it. So since it doubled, tells me that the nitrite is first order. Okay, look at trial 2 to 3. You kept nitrite constant. You doubled your ammonium. What happened to your rate? Same thing. Ignore all of this, so it's just 54 divided by 27. It doubled. It is a first order in the ammonium. So here is your rate law. So this is the rate law. Typically this is A, question A. Then question B would say determine the value of K and its units. Okay, to figure out K, just pick a trial. Pick any trial. Typically it's the first trial you pick just because it's first, or you can look at easy numbers. But just make sure when you pick a trial, use all the values for the trial. So I'm going to use trial 1. So here's the rate. Plug that in for your rate. Here's your value for your concentration of each. Now, if it had an exponent, you put the exponent, but both of these are just to the first. So we don't have to worry about that. Then you're going to divide to solve for K. Now look at the units. Because this is a second order, you know the exponents are going to be 2 minus 1 or just 1, and so that's why the units of K are just liters per mole, and then you have to go back, check the time. This isn't a per second, this one is a per minute, so that's why it's per minute. Okay, last one we're kind of go through. Now if you look, not always, not so nice and neat. Find a starting place. The bottom line, you have to find a starting place. Find where something stayed constant, because they have to have something stays constant. So trial 1, trial 3, they stayed constant. Okay, so what happened then? Between trial 1 and trial 3, you quadrupled your rate. So then you have to say, okay, so what happened here? So 80 divided by 5, that's a 16. So 4, to what power will give you 16? Well, 4 squared is 16. That's telling you that A is second order. Okay, we figured out one of them. Now, here was the problem. I don't see where they held A constant. So now we're going to have to know this fact that we know A is second order to help me figure out B. So between trial 1 and 2, what did A do? Okay, numbers aren't going to be nice and pretty. We definitely round. 10 to 20. That's close enough to 20. A doubled. So you're going to say, okay, A doubled. Well, I know A is second order. I just figured that out. Okay, what did B do? B also went to, that's close enough to 4, B doubled. And then, okay, what did my rate do then? My rate increased by a factor of 16. So you need to figure out, okay, what's the missing exponent? Well, this is 4. So 4 times 4 is how I'm going to get my 16. That's telling me then, that's how I can figure out that B is also a second order. So the rate law then would be K, A to the second, B to the second. Now to figure out the K, I'm just going to pick trial 1 again. You're going to plug in your values. And this time, don't forget, and this is really, really important when you do your math, don't forget to look at the exponents. And it's really easy to forget that you had to square that. And then you're going to divide to figure out K. Now look at this overall rate order is a 4th overall. So that's why 4 minus 1 is 3. That's why my exponents are 3 in my constant as we go through it. And this is a way, okay, remember this shows up in the test a lot, and it's just for formatting that we know liters per mole per second. But it's harder to write that sometimes, so that's why you see it as a -3 and a -1. That just means it's per mole per second, but it's just the shortcut of formatting way that we're going to write that. Okay, so what you can be working on then the rest of the time and helping each other, use your books. Finish page 5. If you look at, there's more doing the rate laws. And then you're going to do the book problems on page 6. So that's what we will check, and we come with your questions and what we need to do on Tuesday, and we're just going to look at different ways that we can experimentally determine your rate law. I hope you have an awesome weekend, and I will see you on Tuesday.